The title of this section, I had it up here yesterday. The title of the section was something about using fundamental identities. We didn't really use any identities yesterday, and so that's where we're going to get into some new stuff today. So I strongly suggest that as we go through the lesson, you have your handy dandy out in front of you. And we're using identities today. So you want to look at the back of handy dandy. Does anybody not have their handy dandy with them? I have extra copies as always. Okay. Now just reviewing the identities real quick. Reciprocal, we should be pretty familiar with those. Sine and cosecant, secant and cosine, tangent and cotangent. If you look at the quotient identities, those come up a lot today. It seems like those are always popping up with these types of problems. So kind of get familiar with what those look like. Remember Pythagorean, those are when you have a trig function squared. And then there's like a plus or a minus, maybe a 1 mixed in there somewhere. I'm just trying to give you key things to look at. And then cofunction and even and odd aren't used a whole lot. We'll see those a little bit today, but for the most part, it's going to be those three groups at the top. Now, part of what makes this lesson a little tricky is this. I always put this warning up here when this happens. There could be, sometimes, there could be different ways that you could do these problems. So it's always kind of hard to teach this lesson because I like to show you the way I think about the problem, but that might not always be the way that you're thinking about it. So just know if you get the same answer and you did it differently, that's perfectly fine as long as we get the same answer. Okie doke. Now the directions say to simplify using fundamental identities. All of the identities on the back of handy dandy are considered fundamental identities. So some of these problems today, you're just going to use one identity. Other problems you might use two. Other problems you might use three, or I guess even more than that. So we'll try to kind of start small and then build our way up. Now, example one, and you got to follow pretty closely here. It's not a day where you want to just kind of copy down what I have up here and then worry about it later. You really want to soak in what I'm doing. That way it makes sense and you don't get stuck when you start your homework later. You want to see what this is all about. So example one says cosine of theta, tangent of theta. Now these two functions are technically being multiplied. It's kind of like when you have 2x in a problem, that is technically 2 times x. Same idea here. This is technically cosine of theta times tangent of theta. Now, as we go through these problems, I'm going to try to explain to you, or at least kind of describe, what the thoughts are in my head about how to approach the problem. What you need to do on these problems today is look at maybe just one part of the problem at a time. Look at one part and see if there's any way you could rewrite that one part using an identity of some kind so that it would have something in common with the other part. So I'm thinking in my head, is there a way to rewrite cosine so it has a tangent in it? Or if that's not working, you can start over here. Is there a way to rewrite tangent using one of our identities so that it has a cosine in it? You're trying to get something in common. Now, since we're just getting started, I'm going to just kind of show you what I did on this first problem, and then you can kind of see how this is going to work. I scanned my identities for cosine, and the only identity I can really use for cosine is the reciprocal identity, where I rewrite it as 1 over secant. But if I do 1 over secant, it's not really going to have a tangent in it. Nothing good is going to happen if I do that. So I'm going to come over here to the tangent of theta, and I noticed if you look at the quotient identities, there is a quotient identity that says tangent of theta, or handy dandy uses u, but u can be anything. Tangent of theta equals sine of theta over cosine of theta. Ding, 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 cosine of theta. If I rewrite it like that, it will have something in common with the first part of the expression. So I'm leaving cosine of theta alone. I'm going to put that part out front. And remember, this is technically multiplication here. So I'm going to multiply by not tangent of theta anymore. I'm rewriting tangent of theta as sine of theta over cosine of theta. If you want to draw a little arrow there, just so you know, that is what tangent turned into. Now, look at what happens. You can put the cosine of theta over 1 if you want to. And then how nice is that? Cosine of theta, they both cross out because they're on that diagonal. And all you're left with is sine of theta over 1. You don't really have to put the 1 on bottom though. You can just write it as sine of theta. So there was only one identity that I used here, and I picked that one because it had a cosine in common with the cosine from the other part of the problem. You're always trying to find something in common. All right, any questions about that one? Okie doke, we've got a few different kinds here, so hang with me. Example 2, tangent squared of x minus secant squared of x. This one is a little bit different for a couple reasons. One reason is that the functions are squared, and so that is different. But even a bigger reason is that the functions here are being subtracted, and up here they were being multiplied. The multiplication is kind of nice because a lot of times you get something like that to happen. You can cross something out and it simplifies really nicely. You're not going to have anything cross out like that when subtraction is involved or addition. It's not really going to work the same way. So let me kind of explain what else I'm thinking about this problem. I'm trying to give you key points here, things that you should look for. I'm noticing these trig functions are squared and there is a minus sign involved. Trig function squared with a minus sign. Anytime I see something like that, I'm going to try and match that up to a Pythagorean identity. If you look at all of our Pythagorean identities, all of the trig functions are squared, and they all involve either a minus sign or a plus sign. And so that, again, is just kind of something you want to get used to, things that you want to look for. Now, unfortunately, and I'm going to pull my handy dandy up here so we can look at this together. Unfortunately, and this is kind of the area that we would be looking, because this is where they have tangent squared and secant squared. But unfortunately, none of those have it in the order that we need it in. We needed tangent squared minus secant squared. Now, I told you this a while back, but in case you forgot, all of these identities right here are equivalent. It's all the same identity, but written in a different order. For example, to get from the first identity right here to the second, all they did was they subtracted the 1 to the other side. And that's how it turned into tangent squared equals secant squared minus 1. It's the same identity in a different order. Well, the order that we need is not up here. So what we'll have to do is we'll have to take one of those. It really doesn't matter which one. I think I went with the second one right here because to me that one looked easier to work with. I'm going to take that second Pythagorean identity. You might want to write this part down in your notes. And I'm going to rearrange that so it matches up to what I'm actually needing in this problem. I need tangent squared minus secant squared. So what could I do to this equation to get it in that order? Subtract secant squared. You can do that with any of your Pythagorean identities. Now it says tangent squared minus secant squared equals -1. And that's all we need because we have tangent squared minus secant squared, so it's just going to equal -1. If it's got a trig function squared, or a couple of them, and a plus or a minus sign somewhere, go for the Pythagorean identities. And it's okay if you don't see it right off the bat. You might have to rearrange a few of them. Okie doke. Any questions so far? All right, we're moving here. Example 3. They're all a little bit different, so make sure you watch on each one. There's a secant squared of x times 1 minus sine squared of x. Secant squared of x times 1 minus sine squared. Now, a lot of times in math, when we have a single term times a quantity, a lot of times we want to distribute, but if you distribute here, you might be making a little bit more work for yourself. It could work eventually, but what I'm noticing right here is kind of what I noticed on the last problem. There's a trig function squared and a minus sign and a 1. So I'm going to try and match that up to a Pythagorean identity. Now, does anybody see what 1 minus sine squared equals? Cosine squared. If you're not seeing it, it's right here. 1 minus sine squared is cosine squared. So let us replace, I'm not touching this part, that part is still there, but let's replace what was in parentheses with just cosine squared of x. Okay, well, we're getting somewhere. Now, even though these trig functions are being squared, what do we know about secant and cosine? They are reciprocals. Now, if the squares are throwing you off, let me explain something real quick. going back and forth a lot today, but this is something nice you can do with the reciprocal identities, or actually you could do this with the quotient identities as well. You can use those even if the trig functions are being squared. I'm going to try to write on this and we'll see what happens, okay? For example, I'm using cosine and secant with this example, so I'm going to go with these right now. Cosine of u equals 1 over secant of u. You can take that identity and you can square everything in it. You can also say that cosine squared of u equals 1 over secant of u. That's still okay to do, and it's still technically a reciprocal identity. Or if you do that with this one, you can also say secant squared of u equals 1 over cosine squared of u. You can use those or these even if the trig functions are being squared. Now, having said that, there's really two different ways that you could finish this problem, and I'm going to show you both ways. What I did in the PowerPoint was I kept secant squared of x. I didn't change that part, but what I did was I used my reciprocal identity on that part to turn it into 1 over secant squared of x. Now again, there's a different way you could have done this. I'll show you that in a second. But look at what happens. You can put this over 1 if you want to. And then secant squared of x, secant squared of x, those cross out and you actually just get back a 1. So final answer to number 3 is 1. All right, on all of these problems today, your final answer should either be a number of some kind or just a single trig function. It shouldn't have sine and cosine or something like that. It should just be one single trig function, or it could be a number like what happened right there. Now, the other way this could have been done is to replace secant squared of x with 1 over cosine squared. Leave cosine squared alone. That is a C. So then if you put that over 1, very same thing happens. You still get back a 1. That's just doing it a little bit differently. That would be replacing that with the reciprocal and leaving that part alone. Okie doke. Any questions on number 3? It's one of those days where I show you a bunch of stuff and then we hope that it sinks in, so when you get to the homework later, you're able to get started. Now, for these problems, if you try something and it doesn't work, then just start over and try something different. I do that a lot. As I'm working on these, I'll do something that I think is right, but if I see toward the end it's not really working out right, then I'll just start over and try something different. Okay, number 4, cosecant of theta divided by secant of theta. Okay, now what I would do first is try to think about what these would have in common, and I'm not really getting anywhere with that. Cosecant would be the same as 1 over sine, and secant would be the same as 1 over cosine. It's not really giving me anything in common though, so I better check handy dandy real quick. And let me see if there are any other identities that involve secant and cosecant. I'm going to start down here at the bottom. You really can't use the even and odd identities unless you've got a negative with that function, and so I'm not going to be able to do that. You can't use cofunction unless there's a pi over 2 minus something in the problem, and I don't have that. You can't use the Pythagorean identities unless you have a trig function squared in it, and we don't have that. They also don't show up right here. I'm looking for secant and cosecant, and they're nowhere to be found right there. So really, the only option on this problem is to use the reciprocal identities. I don't really know where this is going to take me, but I do know that that's really the only thing I could do. Cosecant of theta is 1 over sine of theta. This is reciprocal identities. And then secant of theta is the same as 1 over cosine of theta. Now this looks kind of weird because we're dividing with fractions, but what's our cute little saying for dividing fractions? Keep, change, flip. Let's try that. Keep the 1 over sine of theta, change it to multiply, and then flip the fraction on bottom. That is now cosine of theta over 1. And I'm not really getting anything to cross out like I did right here with number 3. So to multiply those fractions together, I'll just multiply across the top and multiply across the bottom. So right now it says cosine of theta divided by sine of theta. Now, does anybody recognize that off of our identities? Yes, very good. This is a quotient identity. Quotient identity. And so that brings us down to cotangent of theta. A lot of times students have trouble knowing when to stop. Like, when do I know that I'm done with the problem? And again, you're done once you get down to a single trig function, no fractions or anything fancy like that, or a single number. That's when you know that you've simplified it enough. Okie doke. I'm going to keep on going here, so please stop me if you have any questions. We're about halfway there. So number 5, cosine of pi over 2 minus x times secant of x. I say times because, again, those two functions are right next to each other, so that means multiply. Now, I like what I see right here because anytime I see pi over 2 minus x or pi over 2 minus theta or anything with pi over 2 in it, that should match up to one of our cofunction identities. And there's several of them on there, but what does cosine of pi over 2 minus x equal? Sine of x. I'm going to show that up here in case you don't see it. The u in this problem is x for us. So cosine of pi over 2 minus x, that would be the same as sine of x. And so the very first thing that I'm going to do here, too much, Mrs. Street, there we go. First thing I'm going to do is replace that with sine of x. Now, for the time being, I think I just left secant of x alone, but I know I'm not done because I don't have just a single trig function. I've still got two. So then I start to brainstorm, could I rewrite sine so it has something in common with secant? Or could I rewrite secant so it has something in common with sine? You may not get much in common on this problem, but does anybody maybe have an idea of where we should go? Yes, let's use a reciprocal identity. And I'm just going to use it on secant of x. I'll show you why here in just 2 seconds. I'm going to leave sine of x alone, and I'm going to rewrite secant of x as 1 over cosine of x. So where am I going to go from here, or what is that going to turn into? Yep, once I kind of put that over 1 and multiply, now it says sine of x over cosine of x, which is equal to tangent of x. This is a quotient identity. Sine over cosine is tangent. So there were actually 3 identities that we used here. Now again, how did I know to rewrite that instead of that? You're always on the lookout for what's going to happen next. If I rewrite that as 1 over cosecant and that as 1 over cosine, you're going to end up with cosecant and cosine on bottom, and that's not really going to get you anywhere. So again, I'm always on the lookout for what is to come. And the quotient identities pop up a lot. Anytime you've got a sine or a cosine or a tangent or a cotangent, you may end up going that route. Okie doke. I'm going to do 3 more here with you. So, number 6, we're just soaking it in, trying to understand why we're doing this the way we're doing it. Cosine of negative x divided by sine of negative x. Well, what I see first are these negatives. I haven't had that yet today, but I like what I see because anytime I see negative x or negative theta or anything with that negative sign, I'm going to go to the very bottom of handy dandy, and I'm going to try to match that up to an even or an odd identity. Okie doke. So let's work on the top part first. Cosine of negative x. Anybody see what that equals? Just cosine of x. So kind of weird there, but the negative just drops out. And then sine of negative x equals negative sine of x. So right now, we have cosine of x over negative sine of x. Forget the negative for a minute. You can just put that out front if you want to. What do you notice about cosine of x over sine of x? It's a quotient identity. It's cotangent. So you can just leave that negative sign out front. You don't really want to leave it on the bottom anyway. And then cosine over sine is cotangent. So didn't take too much work there. But even and odd identities first, then quotient identity second. You can see how many times the quotient identities pop up. So sine, cosine, tangent, cotangent. Anytime you've got those in the problem, try to look for a quotient identity. All right, last 2 here. This is number 7. cosine of theta times secant of theta minus cosine of theta. I want to compare this problem real quick to example 3 from earlier. Example 3 kind of looked like this. Now I'm going to check my numbers here. That was just by memory. I was right. Example 3 looks like this. You've got a single trig function times a quantity. Now on number 3, I suggested don't distribute because what you had in parentheses on number 3 was a Pythagorean identity. So you did that and then you did not have to distribute. Well, on this problem, what we have in parentheses is definitely not a Pythagorean identity. And in fact, it's not really matching up to any of my identities. So I am going to go ahead and distribute on this problem. And I'll tell you what I see right off the bat. I kind of know that this is the right way to do it because when I take cosine of theta times secant of theta, I'm just going to put them right next to each other for the time being. But I like that because I know cosine and secant are reciprocals. So in the next step, that should work out really nicely. So I think distributing is the way to go. Now when you take cosine of theta times cosine of theta, you could just write that as cosine squared of theta. Now again, we're not done until we get down to a single trig function or a single number. But why don't we go ahead and kind of do what I mentioned earlier, use a reciprocal identity to simplify this first part. Now, there's 2 different ways you could do it. I'm going to leave cosine of theta alone. And I am going to rewrite secant of theta as 1 over cosine of theta. The other way to do this part would be to rewrite this as 1 over secant and then leave secant of theta alone. You'll get the same answer either way. And for right now, I'm just going to bring down the minus cosine squared of theta. I'm not going to worry about that part just yet. So notice what happens over here. The cosine of thetas drop out, and I'm just left with a 1 from that first part. All I have is 1, but don't forget, you still have to subtract cosine squared of theta. So right now it says 1 minus cosine squared, but Mrs. Street tells me I'm not done until I have a single trig function or a single number. It shouldn't really be both. So any idea what kind of identity I could use on that? Pythagorean. If you've got a trig function squared with a plus or a minus or a 1 or another trig function squared, that's probably the way you want to go. And so what does 1 minus cosine squared equal? Sine squared. You guys are on it. So that's it. It's okay if your answer is squared. You just don't want to have 2 different trig functions in your answer. Okie doke. Distributing was the way to go there because there's really nothing else you could do. Didn't really match up to anything right off the bat. All right, this is the last one here. Number 8. I may show you a couple ways to do this problem. So once I finish the first way, don't put your notes away yet because I may also have you copy down the second method just in case you have to do something similar to it in your assignment. Now, I do notice that these trig functions are squared. Typically, I only use Pythagorean identities if there's a trig function squared along with a plus sign or a minus sign or something like that. And I don't really have that going on here. So I'll show you in a minute how we could use, I thought I was hearing things, I think they're cleaning outside. I'll show you in a minute how we could use a Pythagorean identity, but watch what we could also do. If you think about your reciprocal identities with that part on top, secant squared of theta could equal 1 over cosine squared of theta. Now, why am I going with this? Because if I look on bottom, using a quotient identity, I could rewrite tangent squared as sine squared over cosine squared. I'm always looking for something that they could potentially have in common, and here I see it. Cosine squared, cosine squared. Now, to really get going, I need to change, flip, to get these things to cross out. So 1 over cosine squared times cosine squared over sine squared. Now that is exactly what I wanted to happen, but I'm still left with 1 over sine squared, and you really shouldn't have any fractions in your answer. It should just be a single term. So I'm going to go back and use a reciprocal identity to make that look a little bit better. What would 1 over sine squared equal? Cosecant squared. Now, before you put your notes away, I want to show you another way to do this, because if this method doesn't work on some problems, you might also need to know this other approach. So watch what else you could do. I'm going to take this fraction and I'm going to leave tangent squared of theta alone on bottom, but I'll go to the top and try to match that up to a Pythagorean identity. And I think I've got one. Secant squared is equal to 1 plus tangent squared. So I rewrote the top part as 1 plus tangent squared. Now, this is a little rule about fractions. If you have a single term on bottom, you can split your fraction up. You can't split it up if there's 2 terms on bottom, but only if there's 1. That's why I chose to keep the bottom the way it was. So here's what I could do. I could put the 1 over tangent squared of theta, then put the plus sign, then put the second part, which is tangent squared of theta over tangent squared of theta. Now, what could I replace 1 over tangent squared with? You could, and that might end up working out okay. There may be an easier way to do it though. What else could 1 over tangent squared equal? Yes, if you just used a reciprocal identity, that would be cotangent squared, and then anything divided by itself is 1. So this right here should match up to another Pythagorean identity. Cotangent squared plus 1. It's actually in the other order on handy dandy, but that's fine. Cotangent squared plus 1 is cosecant squared. So again, you get the same answer, but those were two completely different ways to do the very same problem. All right, feel free to use whichever one of those you like better. All right, we don't have much homework time today. This is T32 though, so you'll want to copy this down. Now remember, tomorrow is Pi Day, but we're celebrating on Friday because all of you juniors will be gone tomorrow. So Friday first thing, we'll go over this assignment. Bring back questions if you have any. Come see me Friday morning if you have a lot of questions. But once we go over that assignment, we'll start our Pi Day celebration on Friday.